Today is November 2nd. It's our 24th class of the semester. Project number 3 is officially assigned. Grab a copy from your table. Project 3 is going to be due November 14. Is that like a Monday? That sound right? I think it's a week from this coming Monday. So this project is due in about a week and a half. Today we're going to cover section 3.2, which is about polynomial functions and their graphs. Any questions on the calendar while we've got it up here? Right, the project is Monday. I think I've got that right. A week from this Monday. Yeah. 8. So typically we start right at the top of the new lesson, right here on page 8. But we're going to make a big old change to the game plan that you have in front of you. In football, this is known as calling an audible. So we're going to jump over to this page right here, page 11. So let's start page 11. And on page 11, you'll see on the smartboard, I've made a change. So cross off the function that's given at the top of page 11 there and change it to the slightly more complicated one that I've written. Okay, and when this lesson plan was written, it was assumed that before we got to page 11, we had covered everything on pages 8, 9, and 10, which we have not at this moment. So there's going to be some kind of going back and forth, and there's going to be questions, and we're going to kind of fill in the gaps together here. All right, so very much out of order today. Here's the goal. The ultimate goal for today's entire lesson is to be able to graph something complicated like f of x equals this function right here. So first of all, last class we talked about parabolas, x to the what? Second. All right, and parabolas are pretty simple. Like besides lines, parabolas are pretty much the simplest thing you could imagine graphing. You can see an x to the 5th term. Well, that sounds a lot more complicated than an x to the squared, or x to the 2nd, and then you've got these other terms there with a 4th power and a 3rd power. So graphing these kinds of things certainly going to be more complex than graphing lines and graphing parabolas, but that's the ultimate goal for today. So first thing that we want to do in terms of thinking about the graph of this guy is to determine the end behavior. Now, end behavior is a phrase you may have never seen before, but end behavior means as x goes to infinity, what happens to the y values? Maybe as x goes to infinity, the y values also go to infinity, and that would mean going to the right and up. Or maybe as x goes to infinity, the y values go to minus infinity, to the right and down. For functions like this, those are the only options. You are either going right and up forever or right and down forever. You cannot do something like, oh, we're going to kind of level off here at the number 7. It is not possible for things that we're studying today. It's either up forever or down forever. And the same thing is true when you go to the far left. The choices are, if you go to the far left, maybe the y values go up forever, or maybe to the far left, the y values go down forever. It is an either or and no other possibilities. Maybe we'll put the word or between. Okay? And so when we say end behavior, that's supposed to remind you of the ends. I mean, there are no ends on the x-axis. It goes forever. But as we head out there in the forever in both directions, we're trying to figure out what the function is doing. Okay? So end behavior, what is the function doing at the quote ends, far left and far right? Okay, so let's see if we can figure out what this particular x to the 5th polynomial is doing. What we're going to do is think about the graphs of some very basic formulas. F of x equals x, f of x equals x squared, x cubed, x to the 4th, and then the negatives of all these, okay? Do you guys know the word kinesthetic? Who can tell us what that means? Kinesthetic. Yeah, has to do with moving your body. So that's what we're going to do. We're going to tap into not the there's like an auditory when you hear, there's a visual when you see, there's a kinesthetic when you move. Right now we're going to tap into our kinesthetic selves. Everybody stand up. So what we're going to do with our arms is simulate each of the graphs, the functions of each of the graphs there. So the first one is f of x equals x. So with your arms, you have both of them. Put f of x equals x. Make sure that your left arm represents the left on the graph. That's minus infinity. Your right arm is up like that, right? Yes, good, good. So in this case, as we go to the far right, what are we doing? To minus infinity or to plus infinity? Plus infinity. And to the far left, what are we doing? Minus infinity. Everybody see that? Okay, arms down. X squared, use both arms. Very good. To the far left, what are we doing? Every answer is either infinity or negative infinity. Those are your only choices. To the left, what are we doing? X is going to minus infinity, but I'm asking about the y's. The y's are going to infinity. To the right, what are we doing? Infinity. I'm only going to ask about the y's, hands down. It's going to be a shoulder workout for you guys today. This is good. X cubed. Do we know what that looks like? Nope. Some of us do. I mean, we probably don't know it as well as the x squared. X cubed. Is that? Okay. So down that way, up that way. Good. So as we go to the far left, what's happening to the y values? Negative infinity. And to the far right, positive infinity. Arms down. We should have stretched beforehand. I don't know. All right, x to the fourth. Do we know it? Looks an awful lot like x squared. It might have some more ups and downs, but ultimately x to the fourth looks an awful lot like x squared. So just show me, I'm asking for x to the fourth, but just do x squared again. Looks like that. So to the far left, what's happening to the y's? Infinity. To the far right, infinity. Okay, so here are some observations. For the x squared and the x to the fourth, they were both doing the same thing, right? But for x cubed, on the one side was minus infinity, on the other side was positive infinity. For the x, on the one side was minus infinity, on the other side was positive infinity. What's the difference? How do we separate the ones that behave the same on both sides versus the ones that do opposite things on both sides? Evens and odds. That's the separation. All of the evens look like x squareds. All of the odds look like x. Okay. Now let's put some negatives in front of all of these. So again, both arms, y equals negative x. Make sure you get the slope right. Yeah, negative x. So we go downhill this way. So to the far left, what's happening to the y's? Positive. To the far right? Negative infinity. Let's do negative x squared, both hands. Just like that. On the left, what are we doing? Negative infinity. On the right? Negative infinity. Negative x cubed. This was x cubed up here. This one's harder to think about, right? So it's not this, but it's this. Negative x cubed. To the far left, what are we doing? Positive infinity. To the far right, negative infinity. And then finally, negative x to the fourth, negative x to the fourth. It's both down. Minus infinity, minus infinity. Okay, good. Go have a seat. Okay. So all of the stuff that we just talked about, the conclusions that we just made, is summarized on one of the previous pages, and you're going to go back there when it's time to just sort of do stuff in your groups, okay? But our big conclusion here, if the power is even, then both sides are doing the same thing. They might both be going up, or they might both be going down, but they do the same thing. If the power is odd, then the behavior is opposite directions. Maybe minus in the front and positive at the end, or the other way. Maybe it goes up to infinity in the far left and down to minus infinity at the far right. And so the way to know, all you need to know is what's the power, even or odd, and is the sign positive or negative, okay? Here's my shortcut way of remembering what's going on. I always think about what's happening to the far right first. For all of the positive things, x, x squared, x cubed, x to the fourth, what was happening at the far right? They're all going to infinity. Y equals x, x squared, x cubed, x to the fourth. It's kind of interesting to just sort of think of like the left hand is really the only one that's doing anything, right, as you jump up the powers, okay? So if the sign is positive, then at the far right, we are for sure going to infinity. Even, odd, doesn't matter. Yes? If the sign is negative, negative x squared, negative x cubed, negative x to the fourth. So if the sign is negative, what's happening at the far right? It goes to minus infinity, which means that the far right is just going to follow the sign. You see it? Whatever that sign is, that's the answer to the far right. To decide what the left hand is doing, that's where we need the even and odds. And all you have to know is that evens is the same and odds is opposite. Okay, so figure out the right first by copying the sign, and then figure out the left by thinking even odd. Okay, putting it all together. This guy right here, all we care about is the highest power. A few pages before this, it's going to describe that as the leading term, the highest power. So the leading term is this x to the fifth guy right here. So don't look at the 5 first, just think about the sign. What kind of a sign does it have? Positive, which means which way is going to positive infinity? Left or right? No, right. The right is for sure going to positive infinity. And because 5 is an odd number, the left is doing the opposite, minus infinity. So with all of that work, we said the right side was positive, so I'm going to get rid of this guy. And the left side is negative, so I'm going to get rid of this guy. So ultimately, if I zoom out far enough, the graph of this crazy complicated function is going to look like that. I don't know what's happening between, maybe lots of ups and downs, but at the far right, up, and at the far left, down. Good? End behavior. Okay, next thing we're going to do is we're going to find x-intercepts. This is an old skill, but we're going to do some new stuff here. X-intercepts is always set what equal to what? Set the y equal to 0. Okay, so that means setting the whole f of x equal to 0, and so that gives us this equation right there, although actually, sorry, it is not that equation anymore. Why don't we just squeeze it right up here, okay? So we're finding x-intercepts by letting the y equal 0. Okay, this is the most complicated equation we have solved this semester. The first technique is to factor out the greatest common factor. What is the greatest common factor in all 3 terms? X to the third. So we're going to pull that in front. And I think there's some room here in step 2. X to the third outside of big parentheses. What's left from that x to the fifth? X squared. Yep, minus 6x is good. Somebody else? What's the last term? Plus 9 is good. Minus 1? I think that's it. Plus 9. Yeah, and still equal to 0. Don't forget that. Once an equation, always an equation. Okay, so we factored out the greatest common factor. But if you can factor more, you should. You want to completely factor. So when we completely factor, I'll just get the skeleton here. All right, so one very quick vote for x minus 3, x minus 3. You can take your time when you're doing homework and practice and all that to get that, but I trust that you can get that. 2x2 box or trial and error, some technique. Still equal to 0. Okay, and it just so happens that x minus 3 is repeated, so why don't we go ahead and write it in shorthand. It's really x minus 3 squared. Good? Okay, and now the answers to this equation are staring at us if we know how to read them. We have 2 things. I'll circle them in purple. 1 and 2. What's the operation between those 2 things? Multiplication. So I'm just imagining 2 numbers. I'm not getting lost in the details. I'm just multiplying 2 numbers, and what am I getting as the answer? 0. What has to be true about one of these numbers? One of them has to be 0. So that's the simpler set of equations we write down. Either x cubed is 0, or x minus 3 squared is 0. Got to be one or the other. Maybe both. One or the other. Okay. There is only one solution to that equation. What is it? 0 for the first one. It's the only number where you cube it and you get 0. There is only one solution to this one. Close. It's positive 3. Right? You got to make the thing in the parentheses equal 0. X equals 3 is the only one that works. So putting these together, we have just discovered 2 x-intercepts. We'll start with the 3. What are the 2 coordinates for that x-intercept? Is it 0, 3? 3, 0, right? X is 3, and the very first step in this process was letting the y be 0. So 3, 0 is 1 x-intercept. What's the other one? 0, 0. That's it. Okay, so let's start putting some things on our graph here. We had 2 points we just discovered. I'll call these boxes 1 each. So let's call that a 1 and this one a 1. And we said the intercepts were 0, 0, and 3, 0. So we'll just put those 2 dots, 0, 0, and 3, 0. Okay. And I'm going to fill something in here. You're welcome to draw this now if you want, but we might end up erasing it later on. This is one of these processes where you make a couple of stabs at it and it gets better each time, but you might not get it perfect the first time your pencil touches the paper. But what did we decide at the far right? What is this graph doing? It's going up to infinity. So again, I might erase this because I don't know exactly it's going to be there. And at the far left, down to minus infinity. So ultimately, whatever it does in between is going to have to connect to those 2 pieces. We might move them later. Okay, next up is to think about, we just did the x-intercepts, now we're going to do the y-intercept. Yeah, that process is old, right? Just plug in 0 for the x. So when we plug 0 in for all of the x's up here in purple, 0 to the 5th minus, yeah, it's going to be 0, isn't it? 6 times 0 to the 4 plus 9 times 0 to the 3rd. So the whole thing is 0, so we'll put that here. F of 0 is 0. So what are the coordinates? 0, 0. And typically you would just plot that and you get another point. But what happens in this case? It's already there. It happened to be an x-intercept. Sometimes a y-intercept and an x-intercept line up. That's okay. All right. And then there's just one last piece to this puzzle. So I'm going to draw some stuff that for sure I do not want you to draw because we're going to amend it. We got to connect to the 2 blue things and we got to hit these green points right here. And we're just going to do some ups and some downs, okay? So here's one possibility. Don't draw it. Something like that. How do we know it is not that? That's right. We found exactly 2 x-intercepts. And if it had looked like this, then we would have found another x-intercept over there. It cannot possibly do that. Agree? Right? Knowing the x-intercepts, it gives us more than just 2 points. It also excludes the rest of the x-axis from getting hit by this graph. Pete? Term? So I was hoping you weren't going to call me out on that. Yeah. Okay. So let's get rid of this guy right here that I said it cannot be. So let's talk about it. I promised you guys that whatever the power is, that's how many solutions the equation has. So how many solutions should this equation have had? Should have had 5. How many did we have? We had only 2. So where are the other ones? Well, they're there. You're not necessarily going to like them as a technicality, but there are 5 solutions to this equation. Yeah, here, look. We decided to put these 2 together, right? We called it squared. But just don't do that. What's the answer for the last one equal to 0? 3. What's the answer for the middle one equal to 0? 3. Don't get distracted by the fact that it's the same number. Those are 2 answers, right? It appeared twice. And x to the 3rd, isn't that a shorthand too? What is that? X, 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 right? What value of x makes that 0? 0. And this one, 0, and that one. So it's 3 appearances of the 0, 2 appearances of the 3. And it's not just going to be a technicality. It's actually going to help us with the graph of this guy. Good question. Okay. All right. So we've eliminated one possibility. It couldn't do that. All right. Well, look. So if it doesn't do that, then I guess, and again, don't copy this one either. Then maybe it does something like this, where like it hits there, and then it hits here, and now what? It's not going to work, right? This is one of these things where it's like connect all the dots, but don't draw over a line that you've already drawn, right? We're impossible now. So it can't be that. And I feel like, I mean, I got to connect to that, but as soon as I go through here, I'm done. Do you see that there's another option? There's another way to hit that. Isn't it possible that it just barely hits this guy, and instead of continuing through, which gives us an impossible solution, it says, oh, I'm just going to turn around. Absolutely. All right, so we're not drawing any of these yet, but Pete says, couldn't it do this? Missed it. Couldn't it do this, hit at the origin but not go through, and then back up and through? Isn't that another possibility? I think those are the only possibilities. There's got to be one of those things. So we got to decide which one is it. Which one goes through and which one bounces? Yeah, so there's going to be some stuff that we cannot do at this point, and finding min and max is one thing we cannot do. We'll talk about it in a minute. All right, what's that? You could absolutely pick a point, right? Couldn't you just figure out, like pick a number between the 0 and the 3, like 1? Like if you plug in x equals 1, what do you get? That's right. Plug in x equals 1. 1 minus 6 plus 9. 4. So that tells me that the point 1, 4 is on the graph. So over 1, up 4, somewhere up here. So was it the purple or was it the black? Had to be the purple, because the purple is the positive in between, and the black was negative, for sure. We have just pinned it down. I'm going to give you a different way to think about it, which is going to get at Pete's first question about where were the 5 solutions. But absolutely, more points can only give you more information. Yeah. Okay, so here is the last piece of this puzzle. And again, you're going to go through and see the details on a previous page. Let's come back over here to this equation. And we saw that x equals 3 happened how many times? Happened twice, right? That power tells you how many. So I'm going to say there's a new vocabulary word. You'll see it in the notes on the previous page or two. But the multiplicity, go ahead and write this part. Multiplicity in this case is 2. Multiplicity is 2. You got 2 copies of that number 3. Multiplicity reminds me of multiple. You have multiple copies of the 3. How many copies do we have? We have 2. For x equals 0, multiplicity, what was the multiplicity there? It's 3. Okay. All right. And it turns out that's enough information to decide which one of these guys, which x-intercept is a bounce, right? Bounce and then go back the way you came, and which one is a go through. All right, so here's the details. Okay, so coming back up here, I've already drawn this graph. This was x cubed right here. X cubed has exactly 1 x-intercept. It's right there. And did x cubed bounce or go through? Went right on through. Let's think about x squared. X squared also has 1 x-intercept. Does it bounce or go through? At x squared at the origin, it bounces off of the x-axis, right? Doesn't go through the x-axis. It just barely grazes it and then turns back around. Let's do one more graph over here. This last one will be f of x equals x. That one has 1 x-intercept. Did it bounce or go through? Went right through. Okay. So x to the first went through. I'm going to skip this bounce. X to the third went through. X to the fourth we know looks a lot like x squared. So x to the fourth is a bounce. X to the fifth looks an awful lot like x to the third. So what's our pattern here? It's going to go through when? How do you decide that it goes through as opposed to bouncing? It's odd numbers. It's the odd powers. It's the same like even odd stuff here, but a different conclusion. In this case, an odd power like x to the first or x to the third goes right through the x-intercept. But an even power like x squared bounces. And x to the fourth looks an awful lot like x squared and it bounces. So all of the even powers bounce, all of the odd powers go through. And there's only one other thing you need to know about this whole multiplicity x-intercept business. And that's that, would you guys agree? So I'm going to draw part of this here. that suppose I don't tell you that it's x squared, but I just say I've got this function and it's coming in here like this. At this point, would you agree that you really don't know whether it's going to bounce or keep going, right? Like it could do either one. But if I did this, is there any chance that's going to bounce? Like for this to bounce, it would have to like dramatically change behavior, and the things we're graphing don't do that. They're all smooth and curvy. And so if it just goes like a, like a rocket right to the x-intercept, it has no choice but to continue on through. But here, we don't know. It's coming in really slowly, really flat. It could bounce like this one, or it could keep going, like in an x to the third kind of example. And so what I'm saying is that x squared is really flat, x to the third is really flat, x to the fourth is flat, x to the fifth is flat. What's the only one that is not flat at all? Is x to the first. That is the outlier. Every other power higher than x to the first is going to be flat. Whether it's a bounce or a go through, it's going to be flat. But the only one that goes screaming to the x-axis and continues like it doesn't even care, right? It doesn't even pause at the x-intercept, is x to the first. Okay, so let's put it together. And again, this is summarized on a previous page. In our case, we said we have a multiplicity of 3. So first of all, is that screaming through or is that slowing down and flat? That's flat because it's not an x to the first. So let's start filling in. So I'm going to erase the stuff we don't know about. And now you guys are going to draw the rest of this with me here. So we did have the x-intercept there and at 3. And so we decided that because we had x cubed and x minus 3 squared, that was it, right? That at x equals 0, it is going to be very flat. So I'm not going to make any commitment. I could bounce or I could keep going. I can still do either one, but it's definitely flat. And because it's an odd power, does it bounce or does it go through? Odd powers go right on through. And so this guy is going to go up to someplace. But at some point, it's got to come back down because it has to hit here at the other x-intercept. So I'm just going to draw here and I'm going to turn it. And Aaron asked about like local maximum. And the fact is, we don't know where it turns. Someplace between 0 and 3 is all that we can say. I can just about guarantee it's not going to be at 1.5. Like it rarely happens right halfway in the middle. The tools that we need require calculus. It's not something we're going to do this semester. But as Pete says, you could plug in a number, any number you want, and we plugged in 1, and what did we get? No, we didn't get 4. Did we get 4? Yeah. Oh, we got 4. Right. And so 1, 4 is actually up here. So what do you think about my graph? It's not so great, right? I mean, like I missed it. I didn't get high enough. And 1, 4 is almost certainly not the highest point either. It probably goes higher than that. This is just a very rough sketch. If we want more details, we can plot more points. We can use GeoGebra, we can use a graphing calculator. I'm not going to worry about finding that magic point. We don't have a way to do it. Okay, coming over here to x equals 3. It is a squared thing. So is it going to go straight through or is it going to be flat? Any power other than 1 is flat. That is a flat thing. So we're going to come down here and we're going to flatten out. Give myself a little more room here. Come up here, we're going to flatten out something like that. And now I'm prepared to either continue through or to bounce. And in this case, that squared is an even power, which means bounce. And that's really helpful. How did I know it was going to bounce based on earlier work? We had that arrow that was just floating out there. We had to connect it, right? So the bounce agrees with the end behavior arrow that we had. Okay, and then the last thing we'll do here is just check on the graphing calculator. You don't need to do this in general, but I just wanted to see how close we were. What was it? X to the 5th minus 6x to the 4, and then plus 9x to the 3rd. Okay. Zoom 6. What do you think? That looks pretty good right now. Right. So we were not near it sharp enough. Well, we didn't plot hardly any points, right? We just said generally down and left, and up and right. But if we were to change our window here, let's say we focus this guy from something like -2 to 2, maybe? No, that's not what I meant. So all of the action here happens around 0 and 3. So let's focus on, say, I don't know, -2 to 5, and then maybe like -5 to 5. So just kind of honing in on where the action takes place. Okay, and that's really starting to agree with the behavior that we saw here. Flat at the origin, right? Very flat there. It goes up. Like I said, we didn't get high enough. It's at least up at 4, maybe higher. And then it bounces right there at x equals 3 and then goes up again, right? So to date in our class, this is one of the most complex processes that we have had. But like just about anything else in life, with practice, it gets easier, right? So what you're going to do, yeah, Matt?
Do the amount of, I've noticed this, I don't know if this is true or not, but what it's raised to, does that affect the amount of curves it has? Because that has 5 spots on it.
Mm-hmm.
The leading coefficient is next to the fifth. So does that mean the leading coefficient determines how many times the graph curves?
Absolutely. So Matt is leading us to something on page 12 here, which is even labeled as important. So you're going to fill this in here when you get to page 12, but you're not going to page 12 first. You're going back to solidify some of the stuff we just did. So page 8, you're going to do some reading. We're going to let you guys do group activities momentarily here. Let's just fill in this first row of the table together. Polynomial is just something that looks like this guy, x to the third minus x squared minus 2x plus 4. The key that makes something a polynomial is that the powers are non-negative integers. Powers have to be non-negative integers. So for example, if I tried to stick on here a 3x to the -2, it'd say you can't pull that, not with a polynomial. Polynomial has to be positive integers and a constant term. Another thing you could not do would be plus 5x to the 1/2. 1/2 really means square root, right? Okay, what's the problem with x to the 1/2? 1/2 is not a positive integer, okay? So polynomials have these, essentially those are the restrictions. No negative powers, no fraction powers, positive integers only. Okay, that's the stuff we're studying today. The degree, this is just vocabulary, is the highest power. What is the degree for this first one? It's just a number. It's just 3. It's not x to the 3, it's just 3. Just a number. The leading term is the thing with the x in it. It's the whole term that goes with that degree. So x to the third. If there were a 7 in front of the x to the third, then the leading term would be 7x to the third. Okay, the whole term. X to the third there. The leading coefficient we know is just the number in front of a variable. So what is the number in front of the x cubed? It's an invisible 1. Constant term is just the term with no x. What is it? It's 4. And then end behavior. So let's give this a shot. All we care about is the leading term, which is x to the third. We've got it written here. X to the third. Don't worry about the left side, but in the beginning, it's a positive in the front. So that tells me to the right, what are we doing? Up to positive infinity. So as x goes to positive infinity, the function also goes to positive infinity. It's the second blank we're filling in first. And then to decide the left-hand behavior, that's where we think about evens and odds. We know the evens, both the same. Odds are opposite from each other. So if to the right we're going to infinity, to the left we must go to minus infinity. That's our answer there, okay? All right, so what I want you to do is fill in the rest of this table and then keep turning pages. See if you can get all the way through the activity.
Do we want to factor this?
Yeah, for the last one in the table, you'll need to distribute partially. This last one in the table it's already in factored form, but you don't need to distribute everything, not for the purposes of this question. So you can think about, like what's the minimum amount of work I need to do to get the answers to this table. Okay, raise a flag and I will help out. We're expecting lots of questions today.